Hey, Dens, welcome to the start of chapter 20, where we take a look at the sine rule. But before we do, let's talk about essentially what we've learnt in trigonometry so far. This is level 2 trig, which is a step above level 1. Level 1, what you noticed was we dealt with purely right angle triangles. Level 2, we take a look at non-right angle triangles and how to use trigonometry still to figure out the side lengths and missing angles within any sort of triangle. Now, first part, exact values. Most of your answers in this chapter and beyond will be approximations, meaning it's going to be irrational, a lot of decimal places, but there are some answers where we're going to get an exact value. And remember back to surds, exact values are often in surd form or whole number form. Okay, how we come about it is, again, you'll see this in level 3 as well when we put trig ratios in unit circles. But what you see here is an equilateral triangle. We all know that an equilateral triangle will have the same side lengths. So here we've got 2, 2, and 2. We know that trigonometry can only be applied to right angle triangles. So what we can do with non-right angle triangles in level 2 is, in level 2 trig, is just split the triangle in half or perpendicular to a certain edge. So here we've split it in half perpendicular to the edge AC. And then what we notice is we've essentially got 2 right angle triangles. And so within the angles of a triangle, we know it adds up to 180 degrees. All right. And when we split angle B here, okay, this 60 degrees turns into 30. And so using what we know from trig, if we just exclusively look at one of the right angle triangles, so triangle ABD that we took from the equilateral above, you'll notice now that the side length A to D is 1 because the original side length was 2. And angle B that used to be 60 degrees is now 30 degrees since it's been chopped in half. Pythagoras theorem allows us to figure out the side length of B and D, where C squared is going to be 2, and then A squared is going to be the length A to D, which is 1. And so here, this working out is just Pythagoras. And side length B to D, once we figure it out, it's one of the shorter sides since 2 is the hypotenuse, is going to be root 3. Now, there's a distinct relationship between all the angles within a triangle and the side lengths of a triangle. That's something I want you guys to really hone in on. But before we hone in on that any further, we can summarize this triangle here on the right, okay, that we used Pythagoras to figure out B to D. We can write down a bunch of trigonometric ratios for angles 30 and 60. For example, if we were to write down the sine of angle B, which is 30 degrees, as we see here, the opposite length is 1 because that's the furthest side from 30, and then the hypotenuse is 2. So that's everything we learned in the level 1 trig topic, the SOHCAHTOA, the sine, cosine, and tangent ratios. And then if we were to select cosine 30 degrees, well, then we would take the adjacent side length of root 3 and divide that by the hypotenuse of 2. And we do that for tangent 30 degrees and 60 degrees for all 3 ratios as well. And what you notice is we actually end up with a table of exact values. And there's quite a distinct relationship. For example, sine 30 degrees is the same as cosine 60 degrees. And this will make more sense at level 3 trig, where we put it in a unit circle where we've got, 90 degrees, and we can see sine and cosine are just the opposite of one another. All right, so that's sort of a prequel to the next level in year 11 methods. And then cosine 30 degrees is going to be exactly the same as sine 30 degrees. And what you notice is 30 degrees plus 60 degrees equals 90 degrees. Okay, and that will make more sense in a unit circle once we get there. But for now, just know that sine and cosine are opposites of one another. Down below here, we've got 45 degrees, which isn't actually in this equilateral triangle that we split in half. So we can do another triangle where we essentially have the same theorem, but instead we've got a brand new triangle and an interior angle of 45 degrees, which didn't exist in the equilateral. And so when we have 45 degrees, if we were to assume the smaller side lengths were 1 and 1, okay, so this is another part of the prequel to the unit circle, not the sine rule just yet. What you notice is if we use Pythagoras, a hypotenuse is going to be square root 2. And so long story short, we can apply sine, cosine, and tangent ratios to the square root 2 using the 45 degree angle to essentially figure out their ratios. And once again, hopefully you can see here, sine 30 degrees and cosine 30 degrees, sorry, sine 45 degrees and cosine 45 degrees are the exact same. Now, lastly, the tangent's weirdo. It does its own thing. It doesn't complement sine and cosine, mainly because remember when we looked at the circle theorems, the tangent just touches the circle once, which will be explained further in level 3 trig. But for now, what I want you to take away from the introduction to chapter 20 is the angles and the side lengths of triangles are related, okay? And this is where the sine rule kicks in. There's a massive blurb here. So what we're gonna do is we're gonna pick and choose the important stuff, okay? In green, I've highlighted the sine rule, which we'll get to. But the first part I want you guys to understand is the sine rule applies to non-right angle triangles. Okay, so level 2 trig, non-right angle triangles. So here we've got ourselves a non-right angle triangle. What we do is we call the corners capital A, capital B, capital C, but we also call the angle within capital A, capital B, and capital C. Now, what you notice is there's 3 sides, all with lowercase letters, C, A, and B. Just take a moment and see if you can find the relationship between the two. Cool. So hopefully you have identified that little b is on the opposite side of capital B, which is the angle of B. And then little c is on the opposite side of angle capital C. And then little a is on the opposite side of capital A. Now, what does this mean? What I want you to do now is, again, I wish we were in class for this. I want you to go find yourself a ruler and a protractor to measure angles. If you don't know what a protractor is, they're to measure angles. All right, give this video a pause, go find those items, come back. All right, now that you've got your ruler and protractor, what I want you to do is draw a non-right angle triangle, measure the side lengths once you've done so, and then measure the 3 interior angles as well. Okay, so I need you to label all 3 side lengths and all 3 interior angles. Pause the video, go. Hopefully you've drawn those. Everyone's triangle should be slightly different, but what I want you to take a look at is the biggest angle. And now take a look at your biggest side. What do you see? What relationship do you see? Where is the biggest angle to your biggest side? Or where is the biggest side to your biggest angle? Is it the adjacent or is it the opposite side? Well, if it's the opposite, you are spot on. If you said the opposite, you're spot on. Now, I'm not psychic. This is how the sine rule works. Now, let's take a look at your smallest angle and your smallest side. Where is your smallest side to your smallest angle? Again, I'm not psychic, but it's the opposite side, right? It's not adjacent. It's the opposite furthest away to. And then lastly, take a look at your angle that's not the smallest and not the largest, but right in the middle, compared to the side length that's not the smallest and not the largest, but right in the middle. And what's the relationship there? Is that side length adjacent or opposite? It's opposite, right? So that's the sine rule in a nutshell. What it does is it essentially tells us that in triangles, okay, the smaller your angle, okay, the smaller the opposite side length. Okay, the larger the angle, the larger the opposite side length. All right. And we investigated that in circle theorems, right? Like theorem 1, with your different angles. It applies to side lengths as well. Okay, so bear that in mind. This is what the sine rule basically explains. So notice how little b is partnered with big B, all right, and that's they're opposite to each other, and how big C is partnered with little c, and they're opposite to one another. The proof I'm a little bit wary of. I feel like we should learn the how before the why, but essentially what we do is when we have a non-right angle triangle, we can split any side. We can split the angle from A, the angle from C, but here in the diagram, they split from the angle B right down perpendicular to angle AC. We could do the same with angle A and split it perpendicular to the line BC. But if we were to split from angle B to the line AC, what you notice is on this split, because it's perpendicular, we've created ourselves two right angle triangles. So we've got right angle triangle ADB and then right angle triangle DBC or BCD, however you want to read it. What's really important here is you understand rearranging algebraic equations. We're not going to go through it. I think you'll just take my word for it. But what you notice is if we were to have sine A, which is this angle here, the opposite side is H and the hypotenuse is C. So sine angle A is going to be the opposite H divided by hypotenuse C. And then we have this formula here. And then with sine angle C, we have essentially the same thing where we've got sine angle C is going to be the opposite H divided by the hypotenuse A. And so what we do is we can multiply both equations by C and A, and then we get H by itself on the left side of the equal sign. And so what it does is it creates a situation. Hang on, let me think. Do I want to explain this, or is this going to be confusing? Yeah, let's explain it. So what we just spoke about was this, right? So we've got H divided by C equals the angle A. So this angle is opposite divided by hypotenuse, okay? And then we can do that now because we got two right angles. And then in triangle, right angle triangle 2, we've also got, what is it? H divided by A equals sine C. So what we can do is we can move C to the other side in the first equation, and we can have, what's that? C times sine A. And then A times sine C. And what you notice is we've actually got H is C times sine A, and H is also A times sine C. So what does that mean? Essentially, these two things are the same. So we can say C times sine A equals A times sine C. And using some rearranging of this, we get ourselves this formula. Now, if you didn't get that, that's cool. This is just rearranging linear equations. But hopefully you understand this part. This is what we've been doing the last couple of weeks. Okay, so this is just trig. So remember sine A, that is there, sine C, that is there, and then the H is the opposite on the hypotenuse, and that's why we've got these ratios. And how we got these, we're just rearranging. Remember how I said methods is super important? Rearranging is super important to methods. Yeah, literally everything is rearranging formulas, so then you can get various types of pronumerals and whatever you need to find on one side of the equal sign, and you have multiple formulas from one formula. And so we've created this situation. And so this is a sine rule. From all this proof that we did, again, if this doesn't make sense, that's cool. Let's not worry about it too much. We can rub it out. If it makes sense, great. Kudos to you. You essentially will save some time in methods, but after a while, I think everyone will get it. It's not super foreign. But what we do is, once we've established this, well, we can also say, you know, the other angle that we didn't speak about, what was it? Sine B. Yep, that can also be included in this as well. So the sine rule is essentially what we just did with a trig ratio of sine. And this rule here just explains everything that we just did, sketching a non-right angle triangle. Okay. What you notice is the angle and the opposite side of, so the angle and the opposite side of that angle is going to be the same as, or the same ratio as another angle within the triangle and the corresponding opposite side. And the third angle and the corresponding side to that angle's ratio. Okay, so that's the sine rule in short. Now, how do we use this? There's some terms and conditions later on, but how do we use this? Let's put it to an example. I feel like all that talking might have confused us more, but let's go back to our triangle that we sketched. Actually, let's not, because that's done. Okay, that's done with this formula. So how do we use this formula? Let's use it in an example. All right, so here what they do is they ask us a question. In the triangle A, B, and C, where side length A, remember little a is the side length, so all the little letters are the side length, is 4 meters. Side length B is 7 meters, and then angle B is 80 degrees. Now, whatever you do, whenever you see information that's given to you where there's a little b and a big B, they have to be opposite to each other, right? That's what we learned about the sine rule. Okay, so little b, it doesn't matter where you put it. Sorry, big B's angle, where it doesn't matter where you put it, but little b's side length needs to be opposite. Okay, and remember, try and draw it proportional. So don't make B and C larger than A and C, because A and C is 7 meters. B and C is 4 meters. So again, try and draw it proportional to help you out. Okay. Side length A, you can put anywhere you like. And then what we have to do is we have to find the missing side length C. And then they ask us to find the missing angles A and C as well. So let's start with finding A. What you want to do is you just want to use the formula for the sine rule. Now, because they give us little b and big B, we want to use the little b and big B ratio, okay? And we all know that the ratio for each angle and its opposite side are the same to one another. That's the sine rule. All right, so what we do is we plug these values in the best we can. So little b is 7. Sine B is going to be 80 degrees. Little a is 4. But sine A, we don't know what it is. And so you guys are probably asking, well, Ed, why do we use the B here, like little b and big B, and not little c and big C? The reason being is little c and big C, we don't actually have the full ratio. So like we don't actually know what little c and big C are. So that's why we have to use the B ratio that they give us. So they're always going to give you one of the letters angle and degrees. Okay, so here they've given us little b and big B. Sometimes I might give you little a and big A, right? And then little c and big C. But whatever they give you, they'll always give you one set of opposite angles and opposite side length, and then another side length, just to start with. But let's continue with our little substitution that we've done. All right, so we've plugged the numbers into our sine ratio. And so what we need to do is we just got to get A by itself using what we've learnt. All right, so firstly, I know most of us have a scientific calculator, so it'll be good to see what 7 divided by sine 80 actually is. So 7 divided by sine 80 is going to get us 7.10799. Write down as many decimal places as it shows for maximal accuracy. And so let's see, what we can do now is we can get 4 by itself and then multiply both sides by sine A, okay, times sine A, and then we can divide both sides by 7.10799. Okay, so we get 4 divided by 7.10799 equals to sine A. And therefore, if we were to get A by itself, okay, so remember this is like the angle. If we were to get A by itself, we would have to divide both sides by sine, which means we have the sine inverse. 4 on 7.10799 equals to 8. So input this into your calculator. Let me just find it. Oop, that's not it. 4 on 7.10799. This equals 34.246 degrees. Okay, so A here is going to be 34.246 degrees. All right, let's take a look at, so we know this, 34.246 degrees. Now let's find C. Okay, so they tell us to find angle A, find angle C. You better get used to them calling angles with capital letters. That's just how they're going to roll. Right, that's just math for you. Okay, previously it used to be theta and alpha and a bunch of Greek letters. Now they've changed it to capital letters. Right, so we know the interior angle of a right angle triangle, so or any triangle, is going to add up to 180 degrees. So therefore, C is going to be 180, take away 80 degrees, and then take away the 34 point, that looks like 39. 34.246 degrees. Okay, so 180, take away 80, take away 34.246 degrees is going to get us 65.75 degrees. Okay, does it say what we're rounding to? No, it doesn't say what we're rounding to. All right, so that's angle C. And so what you notice is we actually have to find this angle C before we can find little c, because otherwise this here is going to be blank. So what we can do now is we can use our answer from step 2 to find our answer for the side length little c. All right, so plug in the values. Little c we don't know, but now that we know big C is 65.75, we can figure out the remaining. So how do you know if you're using the sine rule correctly? You should have a ratio that's given in full. So here we've got the B ratio given in full to help us find the side length of C. And side length B here is actually 7. So I'm going to sub that in. And then sine B is 80. Let me just, for consistency's sake, keep up the highlighting. And then let's pick a new color. So that gets subbed in there. That's trail of thought. Do we need to color this in there? Let's color this. Let's color everything in while we're on the last step. Okay. So now that we've got just one pronumeral left to find, this one's actually going to be a little bit easier because, well, if we know 7 divided by sine 80 is going to get us 7.10799. So that's that. And then we can multiply both sides by sine 65.75. So what this will give us is, and now there's going to be some rounding errors because this is actually an irrational number that I've rounded to 2. If you press shift answer, you can get the exact. So if that didn't make any sense, that's cool. Don't worry about it. Just type in 7.10799 times sine 65.75. This means the side length C is going to be 6.48. What are we in? Centimeters, meters. All right, 66.48 meters. All right, so that's the side length C. Let me just zoom out to see if we need a quick little summary of what we found. See if we have any more colors left to highlight with. We can use pink. Okay, so the 6.48 is that there. So yeah, we've pieced together every component of the triangle, and that's what the sine rule does. Essentially, this big long proof where we split a non-right angle triangle into 2 right angle triangles, and then we write out the sine ratio for the 2 right angle triangles, and then we do some rearranging magic using our linear equation skills, gets us the sine rule formula, which basically says, let's say A is the smaller side. That means sine A is going to be the smallest angle. If C is the bigger side, then sine C is going to be the biggest angle, and then the second biggest side, B, is going to have the second biggest angle. All right, so that's all the sine rule is, and then we can use that to piece together missing angles and side lengths of a non-right angle triangle, assuming that they give us a pair of corresponding opposite sides and angles. Okay, so here it happens to be little b and big B. It doesn't matter which one they give you; they should give you a pair. But that's the first part. I feel like that's enough for one session. Please have a go at exercise 20.2, just questions 1 to 10. Let me know how you go. Thanks, everybody.